Well, welcome to Gresham College. What better day could there be to talk about the end of the world than the US election? And we planned it meticulously that way. So today I want to tell you about modern scientific ideas about various possible future scenarios for the universe on the larger scale and also more locally on the scale of the Earth and the solar system. This question, although it figures quite largely in lots of the world's great religions, became a matter of serious scientific interest really only in the 19th century. And the reason for that was the Industrial Revolution focused people's attention upon the workings of machines and the efficiency of machines, the extent to which energy was utilizable. And there grew out of that fascination with machines and industry a number of the cornerstones of modern classical physics. In particular, in 1837, Hermann von Helmholtz, German physicist, first wrote down what we now call the conservation of energy. So in the time of Newton, 300 years ago, when he developed his laws of motion and gravitation, the concept of the conservation of energy, and energy was not used by Newton. It doesn't figure in his analysis. He is able to sidestep it. But Helmholtz realized that there was a quantity called energy, which had different forms: energy of motion, potential energy, electrical energy, and so forth. And the total energy budget in any process which took place in the universe could not be changed. However, the conservation of energy allows on its own all sorts of odd things to happen. It allows you to build a perpetual motion machine. If you want to forbid the building of a perpetual motion machine, you have to introduce the concept that there are different qualities of energy energy becomes less and less ordered as work is done using that energy. And this led Clausius to formulate the concept of entropy, a measure of the degree of disorder in energy, and the so-called second law of thermodynamics, which tells us that the amount of entropy or the quantity of entropy in a closed system never decreases. It can stay constant if a system's in equilibrium. It's in disequilibrium, the amount of entropy will increase. So the conservation of energy is telling you, in some sense, that you can't win, and this is a sort of reinforcement of that stricture. Lord Kelvin, William Thomson, in Glasgow, produced a more explicit formulation of this idea when he focused upon what he called the universal tendency of nature for the dissipation of mechanical energy. And he also discussed the consequences of that for the universe as a whole. Helmholtz returned to the question in 1854 and pointed out that the consequences for the universe as a whole is that really there's only a finite future, in the sense that there will come a time when things stop happening in the universe. Time may go on forever, but things will only happen. There will only be dissipation of energy, there will only be increasing entropy, he argued, for a finite future time. Later on, Poincaré showed that in fact there's an even weirder consequence, that if you're in a closed finite universe, eventually everything must recur. There's only a finite number of states to be visited, and in fact, even if you believed this, you might think that on some very, very long time scale, everything would come back and recur. In fact, most of these statements are incorrect in the light of what we now know about the universe. Remember, in the 1800s, this is before the discovery that the universe is expanding. You don't know there's any more of the universe than the collection of stars that we locally call our galaxy. Well, what was behind the thinking of people like Helmholtz and Kelvin was the concept of what I call the steam universe, as it's motivated by these industrial applications. That this measure of the amount of disorder in the universe against time was required to be always increasing. And so if you draw a trajectory of the increase of the entropy with time, there are two implications of this picture that philosophers and theologians and physicists used to wonder about. One was the suggestion to some people that if something was always increasing, then maybe it was going to approach some maximum, some highest possible value, or at least a value so high that nothing could survive, no living system could survive with that degree of disorder in the universe. And that became known as the heat death of the universe. The other curiosity about this was that if you drew a naive increasing picture like this, it suggested to many people that there must have been some type of beginning of maximal order, a state where there was zero entropy, and some people like to call that the beginning of the universe. But after the discovery that the universe was expanding in the late 1920s, there was then a rush of very speculative writings about the far, far future of the expanding universe, and they're associated with a number of quite famous names. Jobius Haldane wrote a book called The Last Judgment, which was about the future course of life in the universe, whether it would survive, what will be the consequences of the ever-increase of entropy. J.D. Bernard, famous Irish physicist and chemist, again like Haldane, a keen communist, wrote a book which tried to explore the way in which life could reformulate itself. So was there a form of life, not like our own flesh and blood, a way of storing information and being alive, which could survive the strictures of the far, far future when all the stars were dying and the universe was becoming more and more disordered? And the most famous name of all is Arthur Eddington, who once wrote an article for the Mathematical Association's annual meeting called The End of the World from the Standpoint of Mathematical Physics. And Eddington, in his usual way, had a wonderful way of characterizing the end of the world. Radio waves were of much interest at that time. Radio broadcasts were made. He called them Hertzian waves. And he said as the universe expanded forever, one of the features of that ever-increasing expansion would be that all radio waves and wavelengths of radiation would be stretched to ever longer wavelengths. So they would become, as he said, like a great broadcast. And so this was his picture of the end of the universe, everything shifting to longer and longer radio wavelengths, a great broadcast. Episodes of Neighbours and The News at 10 distributed all around the universe. Well, this is the motivation from astronomy for those sorts of ideas. Remember, here's a picture of some measure of the separation between distant clusters of galaxies in the universe and time in billions of years. And this shows what we now call the expansion of the universe, the fact that these distant clusters are receding from one another at a rate that increases with time. And we live around about here, about 13.7 or so billion years after the apparent beginning. And the impact of this picture, the discoveries that led to it, is that we live in a universe that is constantly changing. So in the past, it was much denser, it was much hotter. In the future, it will be cooler and more rarefied. If we go back to when the universe was about 300,000 years old, it's 1,000 times more contracted in size. The average temperature is more than 3,000 degrees. And so there are no atoms and no molecules. The universe is not inhabitable by people like ourselves, things that are consequences of chemical complexity. And then there is a historical sequence of events. The first atoms and molecules form, and then galaxies, stars, planets, and ultimately it appears people. But in the future, the long-range forecast looks rather bleak. The stars, like the sun, will eventually exhaust their nuclear fuel. They will, first of all, swell up rather dramatically, vaporize lots of the inner planets in the solar system, and then finally contract dramatically to become little larger than the size of the Earth. And this will be the fate of all stars. So we'll have more to say about this later. So you can see that this heat death scenario that resonated so much with the pessimistic philosophies of the 1920s Dean Ing here in London, a so-called gloomy Dean, was a great theological speculator about the gloom of the end of the world. But even if you didn't like the heat death of eternal expansion, there was an even worse heat death waiting for you if the universe was of this more claustrophobic form. So the alternative to expanding forever was eventually recontracting to a big crunch of apparently infinite temperature and density. So either way, the long-range forecast didn't look very optimistic. Well, first of all, we can just clear up some of these options a little. The picture that people like Eddington and Helmholtz were drawing of the consequences of increasing entropy was not really logically correct. You see, first of all, it is quite possible for the entropy to be always increasing, yet never to have been zero in the past. An exponential curve has this property. It would extend all the way back to minus infinity in this direction. It's always increasing, but it never actually had a zero value. We could have a simple scenario where it did increase and kept on increasing forever. On the other hand, it can keep on increasing forever, yet become bounded in the future. So again, it's possible for a graph to be always increasing, but not to reach arbitrarily high values. So in this universe, the level of disorder is always increasing. In this case, it's increasing, but it's bounded above. There is a maximum possible value. It's also been speculated periodically that something very strange might go on in our universe, particularly the universe that could collapse to a big crunch in the future, that maybe the direction of entropy would change when the universe started to contract, and the entropy would start to decrease again. This, I don't believe, is an idea you should take seriously. This should no more happen when the universe starts to contract than it should happen when a galaxy forms and starts to contract, or a star forms and starts to contract. Different places in the universe would have a different turnaround time for the expansion, and you don't expect the entropy of the universe locally to suddenly be able to know that the universe has started recontracting 100 billion light years away. So this is not taken as a serious possibility. Well, if you're an eschatologist, you have to worry about all sorts of different ways that things could come to a sticky end. It's always good to organise things, so I've tried to organise ends into four sorts. The first is local, the second is gradual, the third is sudden, and the last is temporary. But what I mean by local ends are the things that might happen on this planet, that might even happen tomorrow. And here I'm going to show you an interesting little consequence of statistics. That if the present moment, when we're looking at things, and we're looking at the planet, and we're looking at life and the universe, is random, then it's a simple theorem of statistics that with 95% confidence, anything that we observe now, if it is indeed random, will survive between 1/39th and 39 times its present age. This sounds strange, it's just the application of the normal distribution to events. It's a consequence of assuming that the present moment is typical and random. Okay? And of course, in many circumstances, it won't be. But suppose you apply this. This is a collection of famous events and structures, and these are the times. This is the 1/39th, and this is the 39 times the present age. So what we would expect if we're around at a typical time is that a structure like Stonehenge has got a 95% probability of being around for between 102 and about 156,000 years. The reason why this time for masses became very interesting about 10 or so years ago is that an astronomer used it to make a prediction that the Berlin Wall would fall within a few years. And he was completely correct. Although, of course, every politician and economist and diplomat in the world was taken completely by surprise. Human beings, you see, Homo sapiens sapiens, we've been around about 200,000 years perhaps. On this statistical picture, we've really only got about 5,000 to 7.8 million years to go. So if you were looking at life on Earth from a cosmic perspective, it would not be statistically peculiar if we were annihilated in 5 or 6 or 10,000 years' time. It would be entirely understandable. If we look at Microsoft, you can see the lower bounds are really, there's only 7 months or so that it might survive. The United States also, the United States, 5 or 6 years, and less than, what, about 8,000 years. I put Oxford University at the end, 19 years to 29,000. And also, on the way down, with my calculator, I couldn't help putting Gresham College. And it's 1597, it says on the front of the lecture brochure, so you've got between 10.4 years and 15,873, with 95% probability. Well, of course, it's all very well thinking that humanity might not be around for more than about 5,000 or 6,000 years, but what would be the mechanisms, what could be the causes of their demise? Well, the more we think about it, the more likely our demise seems. There are 2 ways in which life could come to an end on Earth. The first is due to internal forces. We know the possibility of catastrophic war or pollution or disease or nuclear accidents or perhaps climatic change induced by human activity. We're well aware that all these things could produce disastrous accidents. On the other hand, we've come to appreciate that external forces in the long run are likely to be much more dramatic and disastrous. We've come to appreciate that impacts with the Earth of asteroids and comets, some of which may not be visible with any of our present telescopes because they're rather dark, outbursts of gamma radiation, supernovae nearby. In 1987 there was a supernovae in the Large Magellanic Cloud, a dwarf galaxy close to our own. If we had a supernova relatively locally to us here in our galaxy, this could be catastrophic to us. This problem with impacts has become significant enough for the House of Commons to have a standing committee of astronomers who advise on what measures might be taken to try to minimise or counter threats by approaching comets or asteroids. And that's one of the reasons that missions to trying to land spacecraft on asteroids or cometary cores have become of interest. You see, it's very important to know what an asteroid is like on the inside, what it's made of, before you start trying to deflect it or hit it with explosives in the outer regions of the solar system. If it's a single big rock and you hit it very hard, it might break in half, and the 2 pieces go their separate ways and miss us. But suppose it's more like a piece of pumice. It's a collection of millions of rocks all joined together rather loosely. You hit it rather hard and you now have 1,000,000 objects coming towards you instead of one. And you've created an even bigger disaster than you were trying to avert. This picture is a summary, really, of the hazard from impacts. So here is the expected frequency of impacts on the Earth's surface of incoming objects that have these diameters, here from 1 meter up to 10 kilometers. And this is the equivalent amount of energy that they would deposit in the Earth if they struck us direct. So this goes from 10,000 tons of TNT up to 1 million megatons there. This is the size of the object that's coming in, but down here, about 10 times bigger, is the size of the crater that would be created by its head-on impact. And here are some of the consequences. Objects of this very small size, just a metre across, up to about 10 metres across. They're small enough that they'll evaporate and vaporise. They won't make it to the Earth's surface. They may leave lots of dust around, but they won't make a crater on the ground. Up here, you're looking at gradually crater impacts that start to affect regions the size of countries, then the size of continents. They then devastate agriculture, cities, civilizations on the scale of the continent. And down here, just a crater of 100 kilometres across produces enough dust, enough devastation locally, which is thrown up into the atmosphere, to create a catastrophe for almost all living things on the Earth. And here you can see the extrapolated expected frequency of these sorts of impacts from the data that we have, from incoming small objects up here, historical records for more devastating impacts of the sort that killed off the dinosaurs. So this is a very real worry. I think, again, if you're a statistician, you can produce a calculation to show that each of you are more likely to die from an asteroidal impact than you are to die in a plane crash. That's a consequence of the enormous consequences of a large impact. Okay, compared with that, outweighs the fact that you take many aircraft flights, but not many asteroids hit us. This problem of asteroidal impacts, as it were, on another aspect of astronomy. Why we don't see any extraterrestrials writing to us, sending us signals, giving away their presence. So where are they all? Statistically, there ought to be many civilizations, perhaps, in our galaxy and beyond. Why do we not see any signals from them? And people have thought of different reasons for this. It could be that they don't want to contact us because we're too boring, but there are hundreds of thousands of civilizations just like us all over the galaxy. We're like another species of uninteresting beetle. So everything that we do, on the average, has been seen before, and we're not contacted. On the other hand, it might be that we're too special, we're too interesting. And so we're treated rather like a game reserve. We're not interfered with, we're just observed. Because we're so fascinating, and what we do is so unique and unusual, that it mustn't be disturbed. It could be that we're actually too primitive, and that there are conversations going around in the galaxy and beyond all the time, using neutrino beams or graviton oscillations. And there's a sort of galactic club that you can only join by mastering certain levels of technology responsibly. And only when you've done that will you necessarily then reach the level of technical sophistication that will enable you to join the club and join in the conversation. It could be that we are too advanced, that we're in some sense statistically in the lead, and nobody else within communicating range is able to send signals. Why would that be? Well, it could be that, as we've just seen, the effect of impacts is to make long-term survival in the galaxy extremely unlikely. That long-lived civilizations just don't exist. They're wiped out periodically by impacts from comets and asteroids. And we're really rather lucky. We have an unusual solar system. We have a giant planet like Jupiter in the outskirts, which intercepts objects that are threatening once they reach the outer parts of the solar system. A few years ago, we saw a comet collide into Jupiter. Jupiter's gravity is so strong, it captured that comet, it stopped it getting into the interior of the solar system. If things do get into the interior of the solar system, they have to get past the moon. The moon is huge by the standard of planets, moons around other planets. It's almost a double planetary system, the Earth and the Moon. And you can see from the surface of the Moon how many objects have hit it over its history. They would have hit us had the Moon not been there. So we're rather lucky in this respect. Another theory that I have somewhat unusual is that it could be that something like consciousness is actually only a passing phase in evolution. That, in fact, eventually it gets left behind, and the most advanced forms of life in the universe are not conscious or intelligent in quite the way that we are. Stone Age man knew intuitively a lot about Newton's mechanics. If you threw a rock or a spear at him, he would get out of the way. So his brain, through experience, had developed a way of calculating intuitively, rather quickly, what the trajectory of the rock would be. And there are many things like that which we have an intuitive understanding of, even though we don't know the mathematical theory of it. And you can imagine in a very advanced civilization, such intuitive appreciation of things might have grown to encompass the whole of the quantum mechanical nature of the world in the very small. So if life was very small and nanotechnological, it might have a full understanding of the workings of the world on a practical intuitive level without having a scientific understanding of it. So it would have been engendered simply by the evolutionary process. Well, so much for local sudden disasters. What about the gradual fate of stuff in the universe? Well, there are four things that we need to think about. The first are what happens to stars and to galaxies. The next, what happens to structures made out of matter, things like atoms, molecules, solids. And then the fate of matter itself, the building blocks of atoms, protons, electrons. And finally, it turns out, also, above all, the fate of black holes, these great sort of cookie monsters in the universe that supposedly just gobble up material and out of which information cannot escape. Well, the fate of our solar system, unfortunately, is really rather like this picture. This is a Hubble Space Telescope picture of the final stages of a star like the Sun, which is undergoing this explosive red giant phase. You can see it's throwing out energy in two directions, almost in two jets. The star is embedded deep in the center. Everything around it will have been vaporized by outgoing radiation. The colors are due to the radiation exciting atoms of various sorts, and the colors appear through that emission. Now, this picture shows in a cartoon form the types of physical process that dominate over all others in the future of the universe. In any system, whether it's planets orbiting around stars or collections of stars orbiting around the center of galaxies, there is a gradual winding down process, which is a manifestation of the second law of thermodynamics. That what happens is that the motions gradually slow down, their energy is radiated away, both as ordinary electromagnetic radiation, but over the long term as gravitational waves. And that process makes orbiting systems become more and more tightly bound, until eventually they become so close together that they will turn into black holes. When material falls in to form a black hole, no matter what its properties, what it's like, whether it's brass bedsteads, planets, spaceships, or whatever, when you look from the outside, after the horizon surface of no return is formed, all you can tell about what's inside is what's its mass, what's its angular momentum, so how fast it's spinning, and what is its electric charge. All other information is effaced. The properties still exist if you're on the inside, but from the outside you can tell nothing else. But black holes do not just sit there doing nothing, gobbling up more material. Eventually they will gobble up all the material in their vicinity. Our galaxy will have a gigantic growing black hole at the centre which will eat all the stars and material within the galaxy. But those black holes will very, very slowly start to evaporate by quantum mechanical processes. So what happens is that material tunnels out through the horizon of the black hole very, very slowly. The other way to look at it is that the gravitational field of the black hole is sufficiently strong that it can produce pairs of particles and antiparticles using its own gravitational field energy to do the creating, those particles radiate away, and the mass of the black hole reduces very slowly. This is a process discovered by Stephen Hawking back in 1974. It's usually called Hawking evaporation. It's very, very slow, and you can see here that for a black hole the mass of the Sun, it would take 10 to the 66 years for the black hole to disappear. A black hole the size of an asteroid would take about the age of the universe, 13 billion years, to evaporate. So what's happening here is a sort of recycling of material. Material falls into black holes, it's then evaporated out as radiation, electrons, positrons, other elementary particles. In this process, energy is conserved, and the second law of thermodynamics is obeyed. So when material comes out, it comes out in a simpler, less ordered form. Brass bedsteads fall in, radiation and photons come out. It used to be thought long ago that protons, the building blocks of nuclei that form our bodies, were like diamonds forever. That is, once you had a proton and you sat it on its own in the universe, you would always have a proton. But if you want to join together all the different forces of nature into a so-called theory of everything, this cannot be true. It must be possible for the quarks that sit inside every proton to be able to transform into electrons and positrons, and vice versa. And as a consequence, protons must be able to decay. And here's one of the ways in which they could do it. They can turn into a positron and a pion that quickly transforms into high-energy photons. So I talked about this in the last lecture. So this process will probably take about 10 to the 36 years or more, but it means that any stray protons, atoms that might have escaped this process will eventually be turned into electrons and positrons and photons. Sitting here is a collection of stars, for example, which would then, if they don't form into black holes, they will tend to evaporate. Gradually particles will be thrown out from the interior by occasional meeting, going rather too close to another one, receiving another kick, and they will get dispersed. Their constituents again will evaporate by this process, and we will end up with a universe that contains lots of radiation and those elementary particles which are stable, so they have nowhere to go, nothing to decay into. And they must be the lightest particles that carry certain conserved quantities. So we believe electric charge is conserved in nature. So the lightest charged particle has nowhere to go. It can't get rid of its charge because there isn't a lighter charged particle to decay into with something else left over. And it appears at present that the electron is the lightest charged particle and its antiparticle the positron. So there is a big role for electrons and positrons in the future of the universe, together with photons, neutrinos, other very, very light, weakly interacting elementary particles, together with black holes steadily evaporating. The big mystery about the black holes is what happens to them when they've completely evaporated. What's left? Is there just some relic object of tiny mass, or is there nothing at all? Or is there some singularity or hole in space-time, which is rather analogous to the beginning of the universe? So these are the physical processes. What's the timetable? Timetable involves lots of enormous numbers. You can see, for example, in our own galaxy, planets around stars would eventually be certain to be pulled away from their stars by the gravitational effect of another passing star after about 10 to the 15. So this is 1,000,000 billion years on the average. 1,000 times longer, all the galaxies will have either evaporated into bits and pieces, or 10 times longer, they will have, what's left will condense to form black holes, giving out gravitational radiation. Here's the evaporation time for the protons. Here's the evaporation time for the solar mass black holes. If the whole galaxy turns into a black hole, you're waiting for 10 to the 99 years for them to disappear. Once they start to cluster on the scale of galaxy clusters, you form black holes that are going to take 10 to the 117 years to evaporate. If the protons haven't disappeared back here, they themselves will contract and spontaneously form black holes which then evaporate in 10 to the 122 years. Any ordinary stuff that's escaped all this could eventually jump back and quantum mechanically tunnel to become inert iron, but only after some fantastically long period of time. So this is a rather sort of cocksure picture of what's going to happen, and you've probably got the general message. Okay, things do not look very bright. But there are those unknowns about these types of extrapolation, which makes it much harder to predict the future of the universe than it is to reconstruct the past. There's much more certainty about what the universe was like when it was 1 second old than what it will be like when it's 10 to the 50 years old. And why is that? Well, it can be today that there might be very, very weak forces of nature that have no effect really on laboratory physics or even on the expansion of the universe today. But in the long run, they may win out, and their effect might start to become significant in the very, very far future. If any of the constants of nature, like the fine structure constant or Newton's gravitation constant, are not really constant, but are very, very slowly changing, perhaps imperceptibly so today, then again, in the very long run, this could turn out to be the dominant effect. If gravity were becoming slightly stronger in the future, this might enable things to hold together for longer. If gravity is becoming very slowly weaker, this might make everything fall to pieces rather sooner. The reason why everything is so much more difficult to predict in the future is that things are becoming farther and farther away from equilibrium. When we go back to the beginning of the universe, everything becomes a big soup. It's like looking inside an oven. The only thing you can know about an equilibrium system is its temperature. When you know that, you can work out everything else about it. But in the future, things are not colliding in equilibrium with everything else. And if something explodes in one part of the universe, it may not affect things somewhere else, and you end up with a difference in temperature between different places. So the universe becomes much more complicated as time goes on, and requires many more things to give it a description. In the very, very long term, quantum mechanics, you remember, which tells you only the probabilities that certain events will happen, might try to persuade us that anything that has a finite probability of happening will eventually happen if you wait long enough. And just as we might believe that if the universe began by suddenly starting to expand out of absolutely nothing, there may be a probability that it will likewise disappear back into nothing by the same quantum mechanically allowed event. Well, let me return to the issue of the heat death, because it's still popularly believed that it has a particular form. This has got rather mucky, I'm afraid. And this was a problem that was solved by Frank Tipler and myself back in the 1980s, and the solution really emerges from Hawking's discovery that black holes can evaporate. What Hawking was in effect showing was that gravity itself has an entropy. So entropy is not just carried by radiation and particles being disordered and working great machines, as the 19th century physicists imagined, but the gravitational field itself has an entropy. And in fact, black holes have an entropy. I talked about that in one of the lectures last year, and the entropy of a black hole is given by its surface area. If you do anything to a black hole, you collide it with other black holes, or you throw things into it, its surface area will always increase. Second law of thermodynamics governs it. But this has an interesting implication for the universe. It turns out that one can be in a universe, as ours appears to be, where if you work out the actual entropy of everything in stars and galaxies and radiation, then this seems to be steadily increasing. The amount of disorder in the universe is indeed increasing in line with the second law. But if you use Hawking's discovery, you can work out what is the maximum possible entropy that the universe could have. And that turns out to be vastly bigger. That our universe is far away from being as disordered as it could be. So if you like, we could take all the matter in the universe and reorganize it in a way that would vastly increase its entropy. And it turns out that this maximum possible level of disorder in the universe increases much more rapidly than the actual entropy is increasing. So although we're heading to higher and higher entropy, we're actually getting farther and farther away from the heat death, the maximum entropy that you could have. So it's rather peculiar, and quite different from the old sort of Eddington and Helmholtz picture of the universe. And this is a reflection of the fact that in the future the universe will get farther and farther away from equilibrium, because it's not in a state of complete thermal equilibrium. In recent years, this picture has been changed again. We've discovered that the expansion of the universe seems to be accelerating. This introduces a new ingredient to this story. In an accelerating universe, there is a maximum possible entropy. So you could think that there is another line which is drawn there. And so what will happen at some time in the far future is that the actual entropy line will in some way gradually approach the maximum possible. And at that stage, you could regard the universe as being in a sort of lifeless, complete thermal equilibrium, that it would suffer a heat death. Well, the last collection of things to look at about what's in store for the universe in the future is what will happen to the expansion itself. So we've seen that there's the possibility you might head for a big crunch. What would happen to the shape of the universe? We expand fantastically spherically at the moment. 1 part in 10 to the 5 is the accuracy in every direction. Will we head further and further from equilibrium? We'll be able to predict what happens. Now, the universes that are heading for big crunches, the idealized one that we've thought about is rather like this one here, where everything begins expanding at the same moment, reaches a maximum size, and then everything heads back to a big crunch, all in the same way wherever you are in the universe. The real universe is not like that. There are places where the density is higher than the average, galaxies, intergalactic medium. Even if the universe begins simultaneously everywhere, or nearly simultaneously, what will happen is that the denser parts of the universe will hit their big crunch sooner, and perhaps a lot sooner, than the sparser places. So the end of the world is not simultaneous. So the people here can send a signal at the last moment, rather like the last pages of the restaurant at the end of the universe of Douglas Adams, so you can tell other people about what's happening. So non-simultaneity of the end of the world is something to bear in mind. But the thing that most people worry about is, can life in some shape or form continue into the far future? And we don't want to think of life as being like us, necessarily, but we might try to just determine what might be a necessary condition. If you want to have life of any sort, what would have to be okay in the future? And we might characterize life like the artificial intelligentsia do, as some type of processing of information. And the processors may be based on DNA molecules as the hardware, or it may be something more exotic. But if we want to live forever, perhaps the easiest way of characterizing living forever is to say, can you process an infinite number of bits of information to the future? And you would regard that as being a necessary condition of living forever. And it turns out there's a simple answer to that question, and it just relies on whether the universe has one simple property or not today. And it's a property we've met before in these lectures, and it's whether the expansion of the universe is accelerating or decelerating. So a universe where the size against time trajectory has this sort of rather concave picture is decelerating. Effect of gravity, it puts the brakes on the expansion and slows it down. But we discovered back in 1987, that the expansion of our universe has about 5 or 6 billion years ago begun to accelerate. So the curvature of this trajectory has started to tip the other way in this convex direction. So we believe at present that we live in an accelerating universe. And if the dark energy which drives that acceleration doesn't decay, we don't think it would have anywhere to decay to, it will keep on accelerating forever. And unfortunately, it's best to live in the slow lane, because in an accelerating universe, life always dies out. So if you characterize it in that minimalist way as just the processing of information, that any form of information processing will eventually not be able to keep pace with the expansion of the universe. It will not be able to operate, and there will only be a finite number of bits of information processed in the infinite future. But if the universe decelerates, then life in some abstract form, in the form of processing information, can survive forever. You can have an infinite number of bits of information processed to the future. So how would you do that? Well, here's a general idea of how that might be possible. You see, as you go to the future and expanding universe, it doesn't expand perfectly spherically. Some directions expand a little bit more rapidly than others. And what that means is that if the radiation moving in one direction is compared with the radiation moving in another direction, they cool at slightly different rates. You can think of the wavelengths as being stretched more rapidly in the directions that expand faster. So in the directions which expand fastest, the radiation cools quickest. In the directions that expand more slowly, the radiation cools slowest. And in the sort of in-between worlds, it does the in-between thing. And so once you have different temperatures in different directions and different places, you have an energy flow. As you put a piece of ice in this room, heat will travel in such a way as to equalize the temperature, okay, going from hot to cold. So you see here, there'll be an energy flow in this direction, in this direction, and this direction. And once you have an energy flow, you have a way of driving a machine or a processor. You are generating entropy. You are able to process information. Well, the second last, the sudden examples, these are rather alarming. Modern physics allows very dramatic things to happen. So the world could come to an end in a few seconds' time, completely without warning. Our understanding of particle physics is that there are energy levels for the states of matter in the universe, and we believe, naively perhaps, that we are sort of in the bottom floor, that the universe has done all its dropping downstairs from one level to another, and we are in the ground floor, we're in the basement. And there are no lower levels for the universe to suddenly drop downstairs. But we may be incorrect. We may be sort of on the ground floor, not in the basement. And so there could suddenly be a change in energy state of the universe, which, if it occurred, would change the properties of all the elementary particles around us. So they might all become massless, for example. So all the protons in our body would turn into radiation and light. We would disappear. We would know nothing about it. That's the only consolation. So you don't need to pay off that loan after all. Is it right? I think Frank Close gave a talk a few years ago on this topic, because there was a time when in the United States, I think it was in Chicago, there was great concern, members of the public who had read a paper about this, that high-energy particle collisions at Fermilab might tip the universe over this hill and precipitate one of these disasters. So a committee of inquiry was was created to decide that the probability was sufficiently low from evidence of other things. You see, we're being bombarded by cosmic rays all the time with very, very high energy, and that hadn't produced this effect. So you could be pretty certain that the particle accelerator wouldn't be able to do it either, even if you thought it was a possibility. The other worrying thing is that of the sort of the end of the world coming rather like a thief in the night, here is us travelling forwards in time from the beginning of the universe, and there can be an incoming beam of gravitational radiation heading towards us at the speed of light. In a minute or two's time, it will hit us without warning, and it's just part of the initial conditions of the universe. So sudden, dramatic, unadvertised things can happen. The last collection of things I want to show you are some examples of how you can have an end to the universe that's rather temporary, but things can rejuvenate, maybe in a rather different form. The first is the classic oscillating universe. So this requires the universe to recollapse. It seems rather unlikely for our universe at present. If it does so, it might then re-expand, collapse, re-expand, and so on forever. So this was the classical picture of this type of universe. It's what's interesting about it is if you include the second law of thermodynamics, the increase in entropy requires these cycles to get bigger each time. But unfortunately, if our universe is accelerating, as observation shows, then the dark energy which creates that acceleration will inevitably stop these oscillations eventually, and the universe will be left to expand forever after a finite number of these oscillations. We've also in the past looked at the consequences of the inflationary universe scenario for its structure at the present. You remember this was a picture in which we imagine small fluctuations at the beginning of the universe, soon after the expansion begins, and these undergo dramatic acceleration for a short period of time. One of those bubbles that expands rather a lot in this process comes to encompass the whole of our visible universe today. And we can predict in enormous detail what should be the fluctuations we would see on the sky in microwave frequencies if this had occurred. And the observations we make indicate with very high precision that this seems to have occurred, so we take it seriously. An extrapolation of this idea, the so-called eternal inflationary universe, shows that it's a consequence of this process that if it's occurred to produce our little bubble, then our bubble has to create within itself the conditions for further inflation of other little subregions, and they in turn will inflate subregions, and so on forever. So we see here our universe, visible universe, being part of an eternal process that has no end and no beginning. So this region which we're in may undergo the fate of which I've spoken earlier, but beyond it there are other regions which will regenerate and things will start again. Here is another more dramatic picture of this process. You can think of these great fluctuations in energy. Every so often there is inflation, you get a hill, and then on that hill a further hill forms, and then another one, getting higher and higher and higher. Well, finally, last two sets of ideas, some very wild ideas, I don't say much about them. Ted Harrison once speculated that sufficiently advanced civilizations would have the capability of actually controlling that inflationary process. They might be able to control what would be the values of the constants and the expansion that those baby universes emerged with. And then others have suggested that perhaps if there is a collapse of part of the universe in that cyclic process, that in that collapse various constants of nature and other properties of the universe might be changed perhaps in a random way, so that when it re-emerges and expands we have a very different type of universe. Some of those universes will not be suitable for life, others will be. Last of all, amusing suggestion that I made a while ago, about the same time as a certain movie came out. Do we live in a simulated reality? So we might think that the thing that we call the universe is really just part of somebody else's simulation. And so it could come to an end at any time, just because they decide to pull the plug or turn off the simulation. It's been pointed out by philosophers that you should perhaps take this idea more seriously than you might have first thought, because if the universe starts to contain advanced intelligent beings who are able to simulate realities with very, very great precision, then simulated realities should become much more common than true realities. And again, looking at it statistically, we are much more likely to be in a simulated reality than a real one. You see, astronomers today produce simulations to try to understand how galaxies form. They program equations of gravity and thermodynamics, and they follow the formation of stars, clustering of stars. But imagine that you really had unlimited computer power, so that you followed not only the formation of stars, but planets, and then on the planetary surfaces you followed the biochemistry that evolved what we call life, and then you started to follow how those embryonic life forms actually start to communicate with one another. So it's just a matter of degree rather than qualitative difference that you could follow in a simulation the whole process by which life develops. And the challenging question for you to think about on the train journey home is that how could you tell the difference? What would be a decisive observation that you could propose to tell the difference between living in true reality and living in a simulated reality? Thank you. Yes, time for some questions. Gentleman there, yeah. I've got this one.
There was a recent new theory called the Big Rip, which suggests that as the universe continues to expand and dark energy gets stronger and stronger, there will come a time when the dark energy will absolutely rip apart all the quarks and electrons and everything. I don't know if you'd like to comment on that, sir.
Yes, there are two versions of this, and I am responsible for one of them, and Richard Caldwell is responsible for the other. Richard Caldwell's version is to point out that if the pressure of this dark energy is a little more negative than the sort that we normally assume is responsible for accelerating the universe, then it could actually start to make the universe contract, and it would head to a sort of a super crunch rather prematurely, with the density becoming infinite finite time in the future. And all you can do is try to make more and more detailed observations of the dark energy to see if the pressure is negative enough. Okay, I think almost certainly it will not be negative enough. Okay, there are very good reasons why it shouldn't be as negative as is required to do that. The thing that I pointed out is that even if it's not negative in this way, Einstein's equations still allow the universe to come to a sudden end, that it's possible for the pressure and the radiation material in the universe to become infinite without it collapsing to zero volume and infinite density. So I call this a sudden singularity, or a big rip singularity of this different sort. So what's strange is that Einstein equations allow the universe to come to an end at a finite time, without everything going crazy. So one attribute of the universe can become infinite in a finite time. This is sort of another story. I think in the new year I'm giving a talk about infinity. So I've just written a book called The Infinite Book, which will come out in January. But it's an interesting question in its own right. What is the attitude of different sciences to predictions that things become infinite? So some sciences regard that as an immediate signal that there's something wrong with your theory. that it's incomplete in some way, and nature doesn't have real infinities in it. Cosmology is a little bit different. It's happy to have certain sorts of infinity, maybe at the beginning of the universe, to allow the universe to be infinite in size. So I think that at the moment cosmology's view is that big rip singularities are an interesting possibility that they expect eventually to rule out, but they remain a possibility.
Recently we heard last year or the year before that an asteroid was coming towards the Earth and we were in dire straits. And then we were told afterwards, oh, we missed it by 7 million miles. How accurate can the mathematicians get about the probability of an asteroid actually hitting Earth? And if they are, it's going to be a high probability. Can't they blow it up and make sure that all the bits going through our atmosphere burn up, or go to where there isn't a high density and goes in the sea?
Yeah, it's a good question. There's a lot of questions really altogether. One of the problems, when you have objects which are moving in a gravitational field, they have this property of chaotic unpredictability. So a tiny uncertainty in how they're moving, the direction they're going, when they're far away, can produce a very large error by the time they reach us. And this is compounded by the fact that once they, as they come towards us, they're feeling the perturbations of all sorts of other moving objects, other planets, and so it's actually very difficult to predict the exact trajectory. Comets are harder still because they're evaporating. They're outgassing, and the mass is changing. And as they get closer to the sun, they're being heated rather more, and they lose more material. So this tracking of objects is quite difficult. Anything moving under gravity, it's not easy to predict where it'll go. Suppose you decided that you would start a space launch business and you would send your garbage into the sun, firing it into the sun. You'd be surprised how difficult it is to hit the sun. You'll not be able to do it. You'll be swung round in orbits. So even if things miss us slightly, if they get captured by the sun, so they end up orbiting around, that's a worst case scenario, because they hit us every time they come round then. So you must be careful not to do the wrong thing. As I indicated, you can hit these things a long way away, try to deflect them, but you have to understand whether they're going to break into many pieces. If they're tiny pieces, that would be okay, but if they're lots of big pieces, that's a disaster, because you would then have to deflect all of those. So this is a nasty problem, in a sense, of knowing what to do, and the things which have low reflectivity, that are rather dark, can be seen only rather late. There's a new wide-field infrared camera to be launched some years' time into space, and this will be our best way to see these objects. So it will be detecting them by their heat output, in effect, like an infrared camera, rather than relying on their optical appearance.
Can't we have Star Wars and big lasers, burning them up before they get anywhere near?
You could, but I think big lasers have not been terribly successful just very close to the Earth's surface. Also, people worry that once any country has big lasers with interplanetary capability, that they might start pointing them downwards as well as upwards. Yeah, but you don't need exotic nuclear weapons or anything like that. You just need to deflect things slightly. There's one up.
Tree of universes there. How does the law of conservation of energy still apply when you're creating so many new universes?
Yes, it does. I mean, we've been through the story, I think, before. The total energy of the whole multiverse is zero. Okay? And in fact, the energy of each of those little expanding regions is zero. There are perfect balances between expansion energy, which is positive, and potential energy of attraction, which is negative. So the net energy of everything always tends to be zero. So it's a curious situation, the fact that the gravitational field itself is carrying some energy which is negative. Just as when we drop something from here, it's got a lot of negative potential energy here. And as the object falls in the gravitational field, it picks up energy of motion, which is positive from this, but energy is conserved. Okay, hello.
Thanks for a fascinating talk on all the possible scenarios that dealt with for physical energy and the end of the cosmos. How do you respond to those like Teilhard de Chardin, who says it's important to, indeed it's essential to take into account not only the physical exterior energy, but the interior energy, the psychic energy which he relates to consciousness, that has evolved as an anti-entropic process, and must take that increase in psychic or interior energy into account when projecting into the future.
Yes, he liked to sort of model this noosphere, as he called it, of sort of mental energy. I mean, the trouble is, it's not obvious how to do this, okay, or whether it's a meaningful idea. I mean, it's very hard to find any way of attacking this problem. The nearest you could get at it in a well-defined scientific way would be to try to think about information, try and characterize what is information in a better way than we have at the moment, and to see what is the fate of information in the universe. Is it conserved? Does it increase? Or whatever. And some of those results I talked about in the end, about whether information processing can continue, are sort of on the edge of doing that. But I think you would regard these results of the sort that if the universe accelerates, information processing comes to an end, that all ways of storing information, whatever the source of that information, would suffer from those problems. So that's all you can say with physics at the present. Just at the left.
This may sound a very naive question. I guess I'm asking it on behalf of my wife. And the question is...
That's very gallant of you.
You've given a very interesting lecture which seems to imply that all things may pass. My wife is certainly one who believes in spiritualism. Is there anything in what you've said that could give her hope that her beliefs are correct? Because many things happen that we observe and can't explain. Have you ruled that out, or have you ruled it in as a possibility?
I don't think anything I said today could help or harm her in any way. One thing you have to remember about cosmological perspectives on the universe of the sort that I've talked about, and cosmological perspectives on the beginning of the universe, the astronomers talk about the universe in a very sort of coarse-grained, average way. Okay, so they're interested in the statements that they can make, and they talk about galaxies and stars and planets. You know, there's a whole population of objects. They're not talking about things in a very specific, individualistic way. We know much more about the shape of the universe than we actually know about the shape of the Earth, and certainly more than we know about the workings of any individual's human mind. So once we start asking questions about people's beliefs or individual motivations, that we don't really have anything to say from this type of scenario. We're just talking about the average coarse-grained perspective on the future of history, not trying to tell individuals what would be their course. I mean, if you try to do that, then you're falling into the trap of becoming an astrologer, you know, where you think that, you know, the whole universe has a sort of a meaning for you, and even directs your future course. You know, it's very interesting, you go to America, if you even suggest that people's actions should in any way be constrained by the government, the state, people are up in arms, you know, it's the revolution. But they're very happy to feel that their lives are constrained by the workings of the stars, and will dutifully go along to their astrologer and have their actions completely constrained by the stars. So I hope that's helpful.
I will pass your message on.
Okay. We shouldn't need to do that.